Hello, and welcome back to my house. I can't believe we had another snow day, but I hope you've enjoyed it and got lots of rest. Today we're going to be finishing up Lesson 4.2 and hopefully taking care of any questions you have on the remainder of that lesson. Remember that your test has been moved from Wednesday to Thursday of this week, so when we see each other tomorrow on Wednesday, any questions you have, if you haven't asked them already, ask them then. I hope that you get a hold of me on Schoology prior to tomorrow's lesson, though. My concern is that when we get together, there will be so many questions and still more material to cover that there won't be time to address everyone's needs. So find me on Schoology before we see each other tomorrow, preferably, if that's possible at all. But anyway, here we go. Alright, we're going to pick up where we left off. We're going to start, this is really on page 240, well really page 240. They start talking about how to experiment well is the title of, there's like a little heading, how to experiment well. And everything in our lesson is going to go from that point to the end of lesson 4.2. Most of what we talk about will be on page 242. I want to draw your attention to the yellow box that says Principles of Experimental Design. That is one of the most important things that we cover in this chapter. And I can almost guarantee you will have an FRQ on your AP test where you will need to pull information from that table. So, without any further ado, here we go. I'm going to go back to the caffeine experiment that I mentioned in my last YouTube video. My research question is, does caffeine affect pulse rate in high school teachers? Well, in order to do that, first I need to identify my population and my sample. My population is obviously high school teachers. Why is it my population? Because that's the group of people I want to learn more about based on my research question. Now, my sample always needs to reflect the population. If it doesn't, I have a bad experiment. In fact, the results may not be useful to me at all. So in my sample, I'm going to say 100 high school teachers and I need to mention, this is very important, that they were selected randomly. And I'm going to be specific. I'm going to say I used a simple random sample. And there should probably be some more information that goes with this. If I were really doing an FRQ on a test, I would say I worked with the teachers in my high school. I assigned each teacher a unique number and then performed a simple random sample using a random number generator. And I selected the first 100 numbers that I found, and that was my sample. But the sample certainly represents the population. Is it perfect? No. I can't say that 100 teachers selected from one high school reflect all high school teachers, but I can say they were selected through a randomized process, and that's something that the AP graders will be looking for. And I can say that they are all high school teachers. They do reflect the population, but then if I were to critique what I were doing, I would say, however, they were all from the same school. This is starting to sound like a convenient sample, and I should probably do better. But anyway, once I've done all of that, when you conduct an experiment, you're going to be usually breaking people up into two groups. All right. So first, I need to decide, okay, what am I measuring, and how do I isolate my response variable from other things going on in this experiment? In other words, how do I make sure that when I collect data, I'm getting data that help me learn about the answer to this research question? If I want to know if caffeine affects pulse rate in high school teachers, I should probably break them up into two groups. The first group would not receive a treatment. I measure their pulse rate at 9 o'clock in the morning. I measure their pulse rate at 10 o'clock that morning, see if there's any difference, and I have I'm sort of baseline. In group 2, they would receive a treatment, and I need to describe what that treatment is. I'm going to say it's a 5 milligram caffeine pill. Alright, that way it's easy to administer that to all these teachers very quickly, and it's consistent in size. This is measurable. Let's see, I would measure their pulse rates at 9 o'clock in the morning. apply the treatment, after I measure their pulse rate at 9 a.m., give them the caffeine pill, measure their pulse rate again at 10 a.m., and now I compare the changes in this group's pulse rate to the changes in this group's pulse rate. And then I could then say, with some confidence, that it was caffeine that was causing the change in the pulse rate. Now, before I go any further, I want to refer to that table on page 242, that yellow table. All right, here we go. That yellow table on page 242 has 4 really important points. And I'm going to do these in a different order. But they have listed for number 2, random assignment. I'm going to talk about last because that is a big topic, and that's what we're going to wrap up our notes with today. All right, first, this is on page 242. It's the yellow box that you see there. All right, again, I'm doing this in a different order from the book. But I will keep number 1 the same. Number 1, we want to, no, I'm not. I'm going to do number 3 first. Number 3. All right. We want to try to control any possible confounding variables. Anything else I have to say about that? All right, so I have to stop and think to myself, okay, what are some other things that could affect pulse rate besides caffeine? Well, how much sleep teachers got the night before could affect their pulse rate. Maybe if they exercise in the morning, their nutrition, whether or not they had breakfast. Let's see, how many hours of sleep they got, what time they went to bed, what time they got up in the morning. All of those things could potentially affect pulse rate of teachers. So, even things like what subject they teach could affect the pulse rate of teachers. So, I want to try to control those things. There are 2 ways to do this. One, I can have the 2 groups just be a total random collection of teachers. However, if I'm comparing a really random collection of teachers over here in group 1 to a random group of teachers in group 2, that's fine. I just want to make sure those 2 random groups look similar to each other. So in group 1 that's not getting a treatment, I notice I'm getting all the teachers who are really athletic, who get lots of sleep at night, who have good nutrition. And the other group, I'm getting teachers who are up late, grading papers, and really tired the next morning and skip breakfast. That's the problem. Because maybe it's not the caffeine that's affecting pulse rate, maybe it's the poor nutrition, the poor sleep time, all that stuff. So one way to avoid any confounding variables is to just make sure the 2 groups are similar. All right, point number 2 I'm going to make. This is number 1 in the table on page 242. All right. We want to use a design. I think I'm borrowing the same language they use in the book. Use a design that compares. Compare being the key word there. 2 or more treatments. Experiment, we're comparing teachers who haven't received a caffeine pill to teachers who have received a caffeine pill. That's fine, but we are using some form of comparison. Let's see, point number 3, this is number 4 on the list on page 242. We want to make sure that there are lots of experimental units. All right. In other words, you want to make sure that your sample is very big. We call this replication. And that that word replication has a few different meanings in statistics. In the context of an experiment or experimental design, when we talk about replication, we're saying, okay, I want to make sure that what I'm getting isn't just by chance. So if I'm working in an experiment and I measure one teacher's pulse rate, maybe that person has just really good genetics and they have a great pulse rate even after having caffeine. Maybe the person I'm working with never has caffeine, they don't drink soda or coffee, and so their body is reacting in a major way to the caffeine pill that they received. So to avoid any crazy responses, things that are very far from the truth, I want to replicate this. I want to perform this experiment on lots and lots and lots and lots of teachers. Because by doing that over and over again, you end up, let's see, I'm going to say the more replication, the more times you perform the experiment, the more experimental units that you have, the bigger your sample. The more replication equals better precision. Alright, now that word precision I'm going to pause and talk about for just a minute. Precision does not mean it's true or that it's accurate. Accuracy means truth. Precision means consistency. So if I were to perform a study and I get some results, I'm not guaranteed that the results are true. True means accurate. When we did our Federalist Papers study in class last week, remember when we all picked 5 different words, and then we counted how many letters were in each of those 5 words, got the average, and put our averages together. When we did that, we did not get the real average word length from that paragraph. That paragraph's average word length, I think, was 4.3 letters, and we got, I think, 5.8, something like that. So we were pretty far from the real number of letters used on average in that passage. But we were precise. Our results were very clustered together on that number line. So even though the true mean word length might have been over here, and all of our results were over here somewhere, this is precise. And even though this is the true answer, it's accurate over here. When we get a big sample, we can still be very far away from what the truth is. But our answers should be very close together. They should be very precise, getting similar results each time we perform the experiment. Now, if you keep getting more and more people in the experiment, you're going to get closer and closer to the accurate response too. But I want to make sure that you know that if you add people to your sample, you're not guaranteed better accuracy, but you are guaranteed better precision. That's a key point for your test. You'll be very glad you remember that word precision on your test on Thursday. All right. Now, there's one last thing in that table on page 242 that we're going to talk about, and then that'll be the end of this video. All right. It's point number 2 in that table on page 242. All right. But it's the 4th one I'm going to make here. It's the idea of random assignment. Okay. Random assignment is a big deal in an experiment. We saw when we did the Federalist Papers study last week that we could never be random. We can try, but it's never going to happen. So even though I may feel like I'm selecting things at random, I'm not. For instance, if I were trying to take the 100 teachers in our school and randomly assign them to one of the 2 groups, either in group 1 where they don't receive the treatment or group 2 where they do receive the caffeine pill, the treatment. Here's the problem. I may have a teacher come up to me, let's say that it's Dr. Drennan. I say, okay, Dr. Drennan, you're in group number 1. You don't get a caffeine pill. Group number 2, Mr. Moreland, you do get a caffeine pill. If I were to do that, I may be, because I know these teachers, or I'm looking at the teachers, or whatever, I may be biased in some way without even realizing it. Maybe I end up putting more females into group 1 than group 2, and it's just a subconscious thing I didn't mean to do. To avoid any bias creeping into my study, there are a few ways to deal with that. The first method that I can use is, what do they talk about first? A completely randomized design. You'll find more information on this on page 245 of your textbook. A completely randomized design is where you are assigning people into the groups randomly. So instead of me looking at the person and saying, you go in group 1 and you go in group number 2, here's how I could avoid bias. As teachers come up to me, I can flip a coin. And if it lands on heads, you go in group 1. If it lands on tails, you go in group 2. And maybe the groups end up being different sizes at the end. That's okay, but they are done randomly. Another way I can do it is to assign a unique number to each teacher. Randomly, I make sure that the pieces of paper are the same size, of course, and then I would pull 50 numbers at random from a hat, and those first 50 numbers I get go in group 1, and all the ones I didn't get, the 50 that remain, go into group 2. Both ways, I'm using random assignment, and that's good. You need to mention that you're using random assignment when you're setting up an experiment, because if you don't, you will lose points on your FRQ on the AP test. All right, another thing that you could use. So again, I would use either flipping a coin or drawing numbers from a hat. Both of those are good ways to do a randomized design. Another way you could do it, the second one they mention in the book is on page 251, and that's blocking. All right, now for blocking, use this if you notice that your sample, you're noticing two very different kinds of people, and you think that there might be a confounding variable involved. For instance, if I look at the 100 teachers that I've selected to be in this experiment, and I realize that there are a bunch of teachers that exercise in the morning, and there are other teachers who don't, and I think that exercise might affect pulse rate, I don't want to accidentally end up with a whole bunch of teachers who exercise in group 1 and a whole bunch that don't in group 2, because that might mess with the results of my experiment. So what I'm going to do is I'm going to take the 100 teachers and split them up by those who exercise in the morning and those who do not. Then I'm going to do a simple random sample in each group of I don't know, you have to make a decision on how many, and then you would end up like with maybe, I don't know, let's say 20 and 20, 20 and 20. These 20 teachers who exercise and these 20 teachers who don't will end up being in group 1. However, these, let me get another pen, the 20 who exercise here and the 20 who don't here end up in group 2. So you end up with group 1 being 20 who exercise and 20 who don't. And in group 2, you end up with 20 who exercise and 20 who don't. And now look, the two groups are very similar. I feel good about comparing them to each other. I've eliminated the confounding variable of exercising in the morning, and I feel better about being able to say that any differences in these groups might be caused by caffeine instead of exercise in the morning. All right, so this is a block design. My block would be exercise, and then I would split them up, make sure that each group has an equal representation by exercise versus doesn't exercise, and then I would perform the experiment. And that's a really smart thing to do when you think you have a confounding variable in a study. All right, now another thing you could do is a matched pairs design. This is on page 255. It's one of the last things they mention in this lesson. Matched pairs, there are two ways to do it. One way is to take two teachers who are very similar. Like let's say that, trying to think of two teachers who are similar in our school. Let's say that you had me, and I don't know, there was someone else about my age, same level of health, same amount of sleep, same nutrition. You just take a step back and you say, wow, there are a lot of similarities between these two guys. I want to compare, I want to put one in group 1 and the other in group 2 and see if there are any differences between the two of them. And I noticed that there's, hey, maybe a female teacher who's 35 and another female teacher who's 35. They both run in the morning and they both have about the same level of nutrition. I want to compare their results. I would do that if you notice that there's somebody in each group who's very similar to each other, and I want to match them up and compare their results to each other. That's one way to do matched pairs. Another easier way to do it is to take each and every teacher, and don't break them up into little groups. Just take all 100 teachers, and I'm not even going to put them in group 1 or group 2. I'm just going to put all 100 teachers in one group, and I'm going to measure every teacher's pulse rate and write those data down. And then I'm going to give every single teacher a 5 milligram caffeine pill. Wait an hour. And then at about the same time, I'm going to measure all those teachers' resting pulse rates again. And then measure the changes. So you've got one group of teachers that you're working with, but you're comparing each teacher's pulse rate to his or her own pulse rate at the beginning of the day. So that's a matched pair. You're comparing a teacher's pulse rate after the treatment to their pulse rate before the treatment and measuring any change. So by comparing a teacher to himself or herself before the treatment, that's also a matched pair design. You're matching a teacher's present data up with their past data. And so matched pairs. All right, the only other thing I need to mention is on page 248, they sneak in the term double-blind. Double-blind means both the administrator of the experiment and the participator do not know what treatments are being applied in this study. Or I shouldn't say that, I should say, if I'm the one conducting the experiment and I see these two groups, I don't know which group is getting the treatment and which one isn't. Likewise, if this is truly double-blind, it's blind on the part of the experimental units also. The experimental units are wondering, am I getting the treatment or am I not getting the treatment? They don't know. So, double-blind helps eliminate some bias. A single-blind experiment is where either the person administering the experiment or the experimental units don't know who's getting the treatment and who's not, or which treatment is going to which group. Somebody, either the person conducting the experiment or the person who's participating in the experiment, doesn't know who's getting what treatment, or if they're getting a treatment at all. Blindness, we call this just blindness, can help remove bias from a study. So if you're looking at a study on the AP test, they ask you, how can we make sure there's no bias being introduced, or how can we improve the study? If you don't see anything in there about there being single blindness or double blindness, that's a good way to beef up the experiment and remove some potential bias from the results. Okay, that's all I have to say in the study, or in the lesson. I said study a lot today, but that's all I have to say for this lesson. So I'm going to stop my lesson right there. There will be homework and reading that I post to Schoology. Take care of that by your test on Thursday, hopefully tonight, and I look forward to seeing you all soon. Enjoy the rest of your snow day, and thank you for finding me on YouTube. Bye.